In this video, we'll cover both sections 5.2 and 5.3. After finishing 5.1 and seeing how we can verify different trig identities and seeing how just the basic list of trig facts can lead to all these different equations, we can't be too surprised that there's a lot more that we can add. So if you read all of 5.2 and 5.3, there are just loads of formulas. I will talk about the sum and difference formulas for sine and cosine. They include one for tangent. It's unnecessary because we can do it for both sine and cosine, therefore get the answer for tangent. Same thing with the double angle formulas. They also include half angle formulas. They remind us of cofunction identities. Again, this is a very, very lengthy section in a lot of ways, but we're going to simplify it and keep it down to these new ideas. So, what we need to realize that these new formulas, what are these formulas about? They're about playing games with our angles. That if we already know trig facts, if we already know values about like maybe sine of alpha, cosine of beta, well, can we find trig values, something like sine of alpha plus beta? Or if I already know a trig value at regular theta, what happens if I double that angle? How can I find the trig function at that new angle? That's really what this is getting into. So again, these formulas get used, have a lot of different purposes, but for us, it's just a little bit of familiarity, knowing how and when to use these. So let's start off looking a little bit from these 5.2 formulas. Again, they're considered both the sum and difference formulas. Our book writes each of these as 2, so that if it's sine of u plus v, notice the parentheses, the u plus v, both are inside, both being added. Sine of 45 degrees plus 30 degrees. That would total give us sine of 75 degrees. We're going to do that problem in a few minutes, realizing that we know the values for sine of 30 and 45, and hey, we could combine those two angles to get 75, so by knowing those earlier angles and the trig values to go with it can help me to find other trig values at new angles. That's the idea we're going. But again, how does this formula work? Well, if we're adding the two angles, u plus v inside here, well, we get sine u cosine v, and then we stick with the plus, cosine u sine v. If it's a minus in between, if it's sine of u minus v, well, we'll still have the sine u cosine v, but then we'll use the minus sign. That's all it is. It's just if the plus goes here, then the plus goes here on this side of the formula. If the minus goes here, then the minus goes here on this side of the formula. Personally, I really don't love that the book used u and v. If we were in class, I'd probably advise you to memorize this formula in terms of alpha and beta. But since, knowing that we're going to have take-home exams, that you could always reference the formula in the book, I thought I should keep using the same notation. But all we'll do, whatever angle we put first, we'll consider that in the place of u, and whatever angles goes in the second place, we'll substitute that in place of v. So the cosine sum and difference formulas, a little different in that you get both cosines and then both sines for each of the different angles, but also notice how the signs flip. That if you've got the plus in between the angles here, it becomes the minus in between the trig functions here. And if it's the minus between the angles, then you'd use the plus. After we get a little practice here, I'll point out similar things here, and we'll realize we can actually prove these identities by using these. So that's the second part. First, just seeing how we use these for both specific and generic angles. And then the second thing, just to realize that having new rules, new formulas, allows for new things that can be proved using your trig identities, new identities that can be verified. So let's already jump right in and start with the problem. Let's start with the generic problem. Given sine of alpha is 4/5 and cosine of beta is, we'll keep this one, our number's a little easier, 3/4. Let's evaluate, and we'll do 4 problems here. We'll do number 1, we'll do sine of alpha plus beta. number 2, and I'm sorry, the evaluate will also have the exact answers here, exact values. This is definitely another one of those sections that some people who have a little extra understanding with their calculator can almost get a little advantage, and I'm not trying to go that way. I want you to understand the formulas and the facts. So we'll find sine of alpha plus beta. We'll find sine of alpha minus beta. We'll do cosine of alpha minus beta. We'll do tangent of alpha minus beta. And then we'll do sine of 2 alpha. So a lot of problems. But let's start off, let's start with this first one in a straightforward way, and then we'll realize that we're going to need these facts regardless. So that when I look at these two given pieces of information, remembering back from a previous chapter, that when we know one trig value, we know them all. So what you will see me do in a few minutes, I'm going to make a triangle for angle alpha, I'll make a separate triangle for angle beta, and I'll use those triangles as necessary. But why would I need them? It almost seems like I have so much of my information already given. But number one is directly trying to get me to use this formula. That's the first thing. I'm just using alpha in place of u, beta in place of v, and now we specifically know we've got the plus. So if we break this down, this will become sine alpha cosine beta plus cosine alpha sine beta. And now we realize, hey, I already know sine alpha, and I already know cosine beta, but I don't know cosine of alpha, and I don't know sine of beta. And while there are other ways to do this, one of the most basic and easy to duplicate ways to do this is to, again, make right triangles for both. I'm going to make a right triangle. Now, especially because we have multiples, be very clear which one's alpha, which one's beta. This is my alpha triangle. And from alpha's perspective, we know the opposite is 4 and the hypotenuse is 5. Do some Pythagorean theorem. Not Pythagorean trig identity, just regular Pythagorean theorem. And we'll get a nice side of 3 for the adjacent side. And now I'll make a separate triangle for beta. From beta's perspective, well, the adjacent is still 3, but now the hypotenuse is 4, and when you do some Pythagorean theorem, you'll get the square root of 7 for the opposite side. So now, I don't have to go through and find all the trig values, but now I can get anything I need from both alpha and beta. I mean, I could literally sine of alpha, well, opposite over hypotenuse, 4 over 5, but that one was already given. Similarly, cosine of beta was the 3 over 4, but now cosine of alpha. Now I need this, but now I need the adjacent over hypotenuse, so I'll get 3 over 5 times sine of beta. So now I'll come here, but I'll do opposite over hypotenuse and get radical 7 over 4. And this is just good habits just to clean this one up. I mean, little things. This would reduce, but we're actually going to get a common denominator if we don't. So I'll get a common denominator of 20, and I'll get 12 here and 3 radical 7 here. And that's what I mean about exact values. Any calculator technique, you're not going to get something like that. You're going to get its decimal equivalent. So we did that one a little bit, I don't want to say we went through it slowly, but trying to point out all the facts. This was begging me to use one of these formulas, specifically this one with the plus. That's what we did. And then we had to use some other facts. Use these facts to make these triangles so we could fill in the missing values. The only difference in number 2 is that will become a minus. So you do the exact same thing. You'd have sine alpha cosine beta minus cosine alpha sine beta. So you'll just end up all the same work, but this will be a minus. So you'll get 12 minus 3 radical 7 over 20. Now cosine, again, you'll realize that as soon as we made these right triangles, we've made all these problems just about cranking out the formula and then plugging in the missing values. So cosine alpha minus beta, well, now I'm using this formula specifically the minus here, which leads to the plus here. So I'm going to end up with cosine alpha, cosine beta, plus sine alpha, sine beta. And just like the previous two of these things, I already knew sine alpha. I already knew, where is it, cosine beta, but I'm missing the other ones. But one more time, the triangle fills in those values. So now finishing this, the cosine alpha was 3/5. The cosine beta was the 3/4. They're being multiplied. Plus the sine alpha was 4/5. And the sine beta was radical 7. Over 4. And now if we clean that up, we'll end up with 9 plus 4 radical 7 over 20. You might think, again, I hope that wasn't too bad. I'm not trying to rush through that too quickly. But now when you get to number 4, now you might think, wait a second, he just said we don't need the tangent formula. But now that looks like one that the book would be begging me to use the tangent formula. But realize you've already done the hard part. You've already put sine of alpha minus beta and found cosine of alpha minus beta. So even at a harder level, just like earlier, if it's tan x, well, it's sine x over cosine x. If it's tan theta, well, it's sine theta over cosine theta. Well, if it's tan alpha minus beta, then it's sine alpha minus beta over cosine alpha minus beta. And even if we had not already done that work, it's not that hard to go through and do that. Find those two values. And that's a very good answer, but nice to clean up that compound fraction. And I'm not worried about the rationalizing, just that the 20s cancel. And that's a very, very good final answer. Okay. Well, now the very last one on this page, like I said, I still have several things I still want us to do and think about here. But the very last thing for this just first page, given this information, asking you to evaluate all of these, well, all these were in some way trying to get us to use the sum and difference. This one is trying to get us to use the double angle formula. That's it. I should have also put in the directions. I kind of just jumped right in here. Typically on a test, in this type of a section, I'd give you this and I'd say evaluate exact values, but I often also give a little extra hint. Use an appropriate formula. And that kind of gives us a hint to think about these formulas. Now, that doesn't tell you which formula. We still have to realize, well, this one went with this formula, this one went with this formula, this one went with this formula, this one combined the two. So again, that doesn't give us a huge hint, but that still at least points us back to sum and difference in double angle formulas. So now we'll use the double angle formula. That if sine of 2 theta is 2 sine theta cosine theta, well, sine 2 alpha will be 2 sine alpha cosine alpha. I'm not factoring the 2 out, everybody. That's a huge thing to realize here. Some people mistake that, but that would just be 2 sine alpha and there would be no cosine. So that's definitely a big part. That certainly makes it different. So realize I'm using the formula. I'm not pulling out a 2, but now I don't need this piece of information. This one is enough. Just having the alpha triangle. So I get 2. We already knew sine of alpha was 4/5. And then we figured out cosine of alpha was 3/5. So we end up with, 24 over 25. Just plugging in from what I had previous. If I wanted cosine of 2 theta, well, now you could use any one of these 3 formulas. We would already know what sine of alpha and cosine of alpha, the same way we use them here. So we could certainly use this formula and just do cosine squared. So we'd have 3/5 squared minus sine squared. So we'd have minus 4/5 squared. And then we just finish up that answer. Okay, so we started off with some generics. Let's realize how we can also do this with specific angles. So let's again, page 2, use an appropriate formula. to find an exact value. Let's do sine of 75 degrees, sine of 15 degrees, and then we'll do cosine of, cosine of 75 as well. And why not? We'll stick 4 tan of 75. I'm doing this again in degrees. The book does some in radians, can always convert, okay? But now the key is, instead of the previous one where you had extra information, and by using that information to make right triangles, you get any information, the key here is to think about what are good known reference angles. How can you use angles that we already know to get something like 75 or to get something like 15? So for problem number 1, I can get 75 by taking 45 plus 30. Now, I know we can do others. We can use 60 plus 15. We could do 70 plus 5. But why am I doing 45 and 30? It goes back to our reference chart, everybody, that when we made our reference angle chart, it's really these 3 angles. These are the 3 keys. These 2 end up coming up with boundaries. So it's really, can I play with these in some way or other angles that go with these? So this one, yeah, if I'm just going to use these, the way I'll get to sine of 75 is I'll treat it as sine of 45 plus 30. And now it's not alpha plus beta like we had here, or u plus v like we had here, but it's that same setup, that you could treat the 45 as the u and the v as the 30. So this will be sine 45 cosine of 30 plus cosine of 45 sine of 30. And now all of these. Here, now we needed the right triangles to fill in the missing values. Some we already knew, but the missing came from here. And this one, every value is coming off of that chart. We know sine of 45 is rad 2 over 2. Cosine of 30 is rad 3 over 2. Those are being multiplied. Cosine of 45 is rad 2 over 2. Sine of 30, is 1/2. So we end up with, this is radical 6 over 4 plus radical 2 all over 4. Okay. Number 2, very, very similar. Well, how can I get 15? Well, instead of 45 plus 30, I could do 45 minus 30. Now the order matters a little more, everybody. It doesn't matter at all if you went 30 plus 45. These things just flip-flop, and you get rad 2 plus rad 6 over 4. It's the exact same thing. No worry there. But to get 15, you got to subtract in the right order. But now realize we have a second option. 45 minus 30 gives me 15, but so does 60 minus 45. So just to change it up, that's what I'm going to do for the second one. For sine of 15, I'll do sine of, again, 60 minus 45. So that'll be sine of 60, cosine 45, minus cosine of 60, sine of 45. Again, this is what I was saying in the chapter 4 videos. You see how much we're using right triangle facts. We're using the reference angle. We're using the reference angles and the trig values that go with them. We're using the Pythagorean trig identity. That was the building that I've been talking about. So let's just wrap up these problems. So I've got sine of 60. We've got that one is radical 3 over 2. Radical 2 over 2 for cosine 45. Cosine of 60 is 1/2. And you'll notice some coincidences here. We'll end up with radical 6 minus radical 2 over 4. Remember, there's other identities, there's co-function identities, and there's other things that are going on here. But that is certainly a good answer for number 2. I'll come up here for number 3 for cosine. Same idea, just use the cosine formula. We'll treat that one as cosine of 45 plus 30. So for number 3, we'll have cosine 45, cosine 30, minus sine 45, sine 30. And again, filling in rad 2 over 2. I'm going a little quick with my values, everybody. I realize that. But you can always pause, take your time, and we end up with radical 6 minus radical 2 over 4. And again, that's exactly what I was talking about. If you know other trig facts, we're not surprised at all that these two equal each other because there is a cofunction identity that connects the two. So the last one here, and we're just about ready to wrap this up. I could do more, everybody. If you wanted 105 degrees, you do 60 plus 45. You don't have to think about it. The formula does everything for you. 105 is no longer in the first quadrant. Everything here, if you start using calculators to get the decimals, everything's positive because every angle up here is in the first quadrant. So they're all naturally positive. But even if you go to the second quadrant and use this formula to get sine 105, doing sine of 45 plus 60, you'll get a positive answer. And it better be because sine is positive in the second quadrant. And if you did that for cosine of 105, you'll end up with a negative. So again, all the formulas, there's nothing else to worry about. It's just about getting yourself set up using good angles that you can find the values for. Sometimes the book will even get outside of the first quadrant. If they want, 165 degrees, they'll do things like, adding a sine of 15 to a sine of 150. They play other games here. So the last one on this page, and just about ready to wrap up this video, number 4. One more time I threw a tangent at you, and I could have picked any of the others. The point is, once you already know values for sine and cosine, you can get anything. So I want tan of 75, I'll do sine of 75 divided by cosine of 75. If I wanted secant of 75, I'll do 1 over cosine of 75. If I wanted cosecant of 75, I'll do 1 over sine of 75. So once again, sine and cosine are enough. So we'll wrap this up. Tan 75, sine 75 over cosine 75. So where were we? Number 1, we had radical 6 plus radical 2 over 4 divided by cosine of 75, radical 6 minus radical 2 over 4. And just like we saw in a previous one, a pretty good answer, a lot nicer if we cancel off the 4's to at least just do that little bit of cleanup. If I wanted cosecant, you'd flip this just like we've always been flipping. You get 4 over radical 6 plus radical 2. Okay, and the very, very last thing here. Again, it's a nice section. There's a lot to read. There's a lot you can get bogged down, but stick with what I'm showing you. Stick with these formulas. Stick with the homework problems. Other information is good. It can be helpful, but this is all that you need. So the last thing I want to finish with is just to realize that, again, this allows us opportunities to verify more identities. So let's verify cosine of pi over 2 minus theta equals sine of theta. I use pi over 2 just because before I was using degrees, I wanted to remind you of radians. But this is another verify. Pick a side. Well, I'll pick this side. Why will I pick this side? Because I've got a formula that'll allow me to work on this. This will become cosine of pi over 2 cosine of theta plus sine of pi over 2 sine of theta. And now, hey, pi over 2, that's 90. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. So this becomes 0 times cosine. And this becomes 1 times sine. And that equals sine. So again, that's just one identity. I know the book has a couple. I believe there's a couple of skill practice problems as well in 5.2, skill practice and example 6 and 7. Give you a couple of more of these. But like I said, just all these problems, trying to get you in different situations. Not knowing the angles, but seeing how you could apply these formulas. Having specific angles, but knowing how you can apply these formulas, and even verifying identities that these formulas can also come up.